Hello everyone, we are Group 5. Our project is called Global Climate Analytics. In this talk, I will explain our goal, data, system pipeline, and what we found from long-term trends and extreme events. Then I will briefly show the data dashboard. Our main problem is simple. To understand climate change and extremes, we need to process many years of daily weather data. So our goal is to build an end-to-end pipeline that can scale. Specifically, we do three things. First, we compute long-term trends like temperature and precipitation changes over decades. Second, we detect extreme events, use clear rules, and count how often they happen each year. Third, we deliver the results in web dashboard so users can compare cities. We use NOAA GHCN daily data from 1950 to 2020, which is about 70 years. It covers over 100,000 stations around the world. The row format is CSV, and each row looks like station, date, element, and value. In our project, we process about 25 gigs subset, around 50 million records, using Spark on GCP Dataproc. For extreme events, we do not rely on single global index only. We design rule-based thresholds based on literature and weather warning guidelines, so the rules are easy to implement and explain. Now I will describe our system. First, we download raw NOAA CSV gzip files and store them in Google Cloud Storage, partitioned by year and station. Second, we run PySpark jobs on Dataproc to clean the data, normalize units and timestamps, and pivot the long table into daily wide table per station. Third, using Spark SQL and PySpark, we compute trend metrics and extreme events indicators, and then aggregate them into station level and city level. Fourth, we export the aggregate results as JSON back to cloud storage. Finally, our web dashboard loads these outputs and support interactive exploration and two-city comparison.
Our stack is PySpark on Dataproc with JCS as the data lake. Dataproc gives us a managed Spark environment. We use a single node cluster with 8 CPUs and 32 gigabit RAM, which is enough for our 1950 to 2020 workload. If we ingest more years or more datasets, the same design can scale to a multi-node cluster. For storage, we keep raw data as CSVJZ, and we write clean data to JSON for faster downstream processing. Here are our main pipeline steps. We read raw CSV.jz files, clean records, and pivot to white daily rows. We also join station metadata such as latitude, longitude, elevation, state, and name. Then we write clean JSON for later Spark jobs. For quality control, we treat -9,999 and invalid dates as missing and remove them. We filter out abnormal NOAA flags like M flag, Q flag, and S flag. We also convert units. Maximum temperature and minimum temperature are stored in 0.1 degrees Celsius, so we convert them to degrees Celsius. Precipitation, snow are stored in 0.1 millimeter, so we convert them to millimeter. We also create derived features, like the temperature, and use average temperature. Now the results. We show an example comparison between Boston and Miami Beach. For temperature, both cities show an overall warming trend from 1950 to 2020. Miami Beach is consistently warmer and its annual temperature range is smaller. Boston is cooler and its range is larger. For precipitation, annual precipitation slightly increases over time, especially after the 1980s. We also see stronger year-to-year variability, meaning more very wide and very dry years. For snowfall, Boston peaks around the 1960s and 1970s, and then declines afterward. Miami Beach stays near zero, which matches what we expect. Next, extreme events. Our method is we set rule-based threshold for multiple variables, including heat, cold, heavy rain, and heavy snow. For each station and each year, we count how many days exceed the threshold. Then we sum them into total extreme events days. In our sample, Both Boston and Miami Beach show high levels of extreme event days across 1950 to 2020. Miami Beach shows a gradual increase, especially after the 1980s. Boston stays persistently high, but it is more variable year to year. The key takeaway is climate change affects not only daily weather, but also extremes.
The demo dashboard, user can select one or two cities. It supports both single city view and side-by-side comparison. We show about 70 years trends for temperature, high or low, precipitation, snow, and extreme events. The charts are interactive. Users can hover to see extracted values and zoom in to check specific periods. All charts are powered by pre-processed Spark results. The dashboard mainly handles visualization. Now let's have a look on our demo dashboard. So here are two blanks. First city, we chose Boston. Just pick one. And the second city, maybe Miami. Miami Beach. And here are the station IDs for both cities. And down below here is a year maximum and minimum temperature for Boston and Miami Beach. And also when you put your mouse on the table, you can see the specific value for the maximum and the minimum temperature. Also here are the functions we set. We can zoom in, just download the plot. And down here is the yearly precipitation. Also here shows the snowfall. So we transfer to extreme events, and it shows the sum of the days that happens the extreme climate events. And it also shows here. When you put your mouse on here, you can see the days in Boston is 27 and 26 in Miami Beach. So we come back to our point and go on.
To conclude, we built an end-to-end big data pipeline on GCP for NOAA GHCN Daily from 1950 to 2020. We cleaned and aggregated daily temperature, precipitation, and snow into city-level statistics. We also designed global extreme weather threshold based on existing studies and national guidelines, and tracked how the frequency changes over time. All results are delivered through an interactive dashboard for long-term exploration and city comparison. In the future, if more data sources are available, we can extend the system with more variables such as air quality or UV index, and create richer visualizations and combine analysis. Thank you. That's our project, Global Climate Analysis.